da oltre 50.000 dermatologi. La salute passa anche dalla pelle.
targets, changing hearts, circles keeping moving us apart. Dee-doo-da, dee-doo-da, dee-dum, dee-doo-da. Dee-doo-da, dee-doo-da, dee-dum, dee-doo-da. Return, there is no return. Forward march, spreading those private faces, framed, lost in memory. Following new action in destiny, knows it where we're going. Keep on moving, changing motion. Keep on moving, lost in motion. Moving targets, changing hearts, painted circles that keep us apart. Moving targets, changing hearts, circles keeping moving us apart. Dee-doo-da, dee-doo-da, dee-dum, dee-doo-da. Dee-doo-da, dee-doo-da, dee-dum, dee-doo-da. You could put some joy upon my face. Oh, sunshine in an empty place. Take me to turn to, and babe, I'll make you stay. Oh, I can ease you of your pain. Feel you give me love again. Round and round we go. Each time I hear you say, this is the rhythm of the night. The night. Oh yeah. The rhythm of the night. This is the rhythm of my life. My life. Oh yeah. The rhythm of my life. Won't you teach me how to love and learn? There'll be nothing left for me to yearn. Come closer and let me hold your hand. I don't wanna face the world in peace. Please think again, I'm on my knees. Sing that song.
Stefano, andiamo? Okay. Allow me to leave the mask. We are quite far away. So, and maybe also for the speaker, if they like, it's probably better to avoid to breathe your CO2, which is one of the main enemy of this day. Okay, so I would like to welcome all of you to this very nice event. And first of all, I would like to thank our colleagues and friends coming from, well, a little bit far. It's becoming far because of the new world, the new life which we are living It was not far 2 years ago. So our colleague from Rolls-Royce and Rotax that have been main partner of this program. And we as University Federico II are appreciating the idea of Tecnam to organize this closing event of this research project funded by the European Union on hybrid aircraft, on this new kind of propulsion. This is a very important topic for aircraft. For all aviation, we have had, well, there is a stress all around the world against the, the climate, the pollution, and we have seen that aviation is not the big enemy. We know that pollution has been created much more by other human activities, but aviation has always the culture for experimenting new things. And that's very important because working on new propulsion systems, it's the main part of having a renewed aviation. The history of the aviation has been the history of the engines, has been the evolution of the aviation, starting from Wright brothers to maybe Charles Yeager and to maybe others, Douglas, for example. The main point has been always the propulsion system. If you have a new propulsion system, you may have a new airplane. You may have a new architecture. And I believe that when we will be able to have new architecture for the airplanes, we can use and profit the most for this new propulsion. We know that all the world on the research is working on this system. And at this moment, there are many ideas. We have electricity, we have hybrid, we have fuel cells, we have hydrogen. So we have many ideas. And this is important because we have to experiment all these things. And we, all together, academics, research center, and industry, we have to work close. And also, just this morning, I had an email from EASA that they were telling that there is new ideas for new rules for vertiports. Vertiports for another activity which is urban air mobility. So, and for all these things, this event is very important, and I would really like to thank you for giving me the opportunity for entering this event. I would like to thank colleagues that have the time for coming here in presence, and also I would like to thank all the people. I know that there are something like 80 people, something like around 80 people linked from outside. I received several phone calls of people excusing, apologies, and so on. Well, we all know all these things, but we have to work straight for the objective, and the objective will be new propulsion system. We were exchanging a few words this morning, and probably it's a long, long pathways. We have many examples so far that tell us that there is a long, long pathway. But this is not fearing us. Absolutely. We are just walking and some way, maybe with some mistakes, which are in the human nature. We will progress and probably for the next future. Before entering the event and let's say starting this and giving the words and the podium to the people that are in the program, I would like to say other few words. Please allow me to give a thought to what is happening in the Eastern Europe. This is something that we cannot forget at this moment, and we hope that science, technology, and maybe also philosophy can tell the people that there are other things to think about, not boundaries. When I see some, let's say, things on or report on the media, on the TV, I am also thinking what usually the astronauts, they say when they come back from the ISS, from the International Space Station, they always say that the Earth is just a little point, and from the space, which is not very far because they are, 400 kilometers from our land, from our atmosphere. They say that they don't see boundaries. This is very important because we are different. We have the culture of the diversity, and diversity is something very important. And we hope, I'm not the Pope, obviously, but it's something that is really touching me. And I have to tell you that in our research group, there is, in this period, always 5 minutes, at least lunchtime, that we spend for thinking about these things. Okay, so thanks for these 5 minutes to Ukraine. And now, our wonderful airplane. Tecnam, as in the logo, we build airplane for passion. and Tecnam is a magic world, and I'm sure that also, I'm not leaving your working environment, but I'm sure that it's very, very similar. And so let's move to this project. First of all, we thank European Union for funding, that's for sure. And we thank the partnership for achieving such important results, which is maybe 5% to reach 100%. But we reached 5%. And the airplane flew, which is something which is a fact. And as an engineer, we like facts. Okay? So, thank you for coming. Thank you all for coming. And I would say we can start. I know that people has plane waiting for them. So, this morning we have the pleasure to invite onto podium representative from Rotax and from Rolls-Royce. And together, the end will be our lovely Tecnam. Fabio, it's our incredible close friend. So please, let me introduce Veit Manninger and Dominik Katholnig for maybe Katholnig, excuse me. Well, my future will be learning Deutsch, learning German language. Yeah, but I'm not sure. There is something close to Latin in the German language, and I was not a big Latinist when I was young student. But anyway, you can come here and talk about your activity in the H3PS research program. Please.
So, welcome to everybody as well from Rotax side. And we will say thank you very much for Tecnam and the university for the invitation. It's a very big pleasure for us to talk a little bit about Rotax in general today, but the main topic is of course the H3PS project. I will talk in general now a few minutes, but I will take it short and crispy, that we are changing to the main topic, and my colleague Dominik Katholnig will then show you how or what we contribute in this project H3PS. To Rotax by itself, we are a engine manufacturer company based in Austria. We have a very long history, and we are a global player, because we are not only manufacturing engines for aircraft combustion systems, we are manufacturing a lot of other engines as well, especially for the BRP products, like Can-Ams, Skidos, jet skis. Maybe the one or other of you already know it, and they are all recreational products, and everybody maybe one time sit on a Skido or a jet ski. But we from Rotax in the latest 70s started to produce aircraft engines as well, and that's the reason why we are here today. Shortly to our company as well, our mother company is BRP in Canada, and we are 100% daughter, but you will see it later in the next slides where we are going through the history. I want to emphasize again for everybody, we are manufacturing engines only and not aircrafts. Yes, you can read it. We have a very long history. We were already established 1920. We started very simple with a gear wheel. And 2 years ago, we had a big anniversary. It's 100 years anniversary. We are going just through some most important events which we have for the aircraft sector. It has been a lot of other events, but it would be too long. So foundation 1920, 1970, first time we made a joint venture with the Canadian company Bombardier. That was the start for the aircraft section. 1982, we established the first aircraft engine by itself. In 2003, there were a big change in the company structure. Bombardier sorted our business out and created a completely new company called BRP. And since this time, BRP, Rotax, the name were established. In 2014, we brought on the market the first full electronical injected engines, the 912 IS Sport, and quick after 2015, already the 915 IS engine. With this engine, we are here participated in this H3PS project. And of course, for our customers, we want to make a present in 2020. We created a special limited edition of our engine. Just only 200 pieces were sold. It was limited. This edition was a 915 IS engine, but with a different style, different design, and of course included different services. In the meanwhile, over the last 10-15 years, when we came together to the BRP Rotax company, we got a company belonging to the Toronto Stock Exchange and to the New York Stock Exchange. We get your heart beating, yeah. That is the main claim, what our employees living for. That is the driver for their motivation in the daily business. We always want to get the heart of our customers beating. Since the beginning, that is that what we are working for our goals and for our personal motivation. I just want to show you a short clip, 20 seconds, that is a summary of all our drivers daily and for what we are working for in the especially aircraft business. Okay, I think pictures say more than words. So that was, we can continue with the next. What are our core markets? Because I think it has to be clarified. We are one of several engine manufacturers. Our core markets are in the fixed wing, gyrocopters and helicopter markets. Everything up to around 160 horsepower. We are not offering and servicing higher horsepower ranges. And in that three markets, we are working since 4 decades and with a good success. Not jumping. Okay. I just want to give you a small insight where we are focusing in and what our goals. That is the philosophy of our aircraft department from Rotax, independent of the other departments. Since the beginning, we always focused, we want to have the best quality, and Rotax is not manufacturing an engine which is not in the end certified. So when we are deciding for anything, it has to be premium and best quality. Next one is independent of the technology, that we want to have the smartest, greenest, most economical and safest aircraft. We want to have the best service, because everybody of you knows we are in the 21st century. It's a century of service. Not only the best product makes you successful, it has to be a combination between service and product. And that's the reason why we started several years ago as well to work with the latest kind of technologies to make our products more successful, like engine control units, full electronic redundant injection system, the BRP utility diagnostic systems. That's some of many, but for the service centers and the worldwide network, we want to have the best service to the end customer, and that you cannot do everything personally. We try to maintain and to educate all our people outside with the latest technology and services, for example, 3D technologies, augmented reality, virtual reality. So we already have a mix. that every end customer all over the world can enjoy the best service and the best educated people. Now, last but not least, I want to show you some facts and figures that underline our success in that core markets where we are in the moment. We are now in the moment working with around 220 different service centers all over the world together. They are specialized on Rotax engines. We have already 190,000 engines sold since we started to produce with production with the first engine. We have flown around 78 million flight hours with our engines in the field. We are equipped in around 450 different aircrafts from different manufacturers. And of course, where we are very proud of it, but it's a lot of work in that sector till up to 160 horsepower, we have still a market share of 80%. So that was shortly for the general information to Rotax, but now we have to switch, of course, to the main part, and I will hand over to my colleague Dominik Katholnig. Thank you very much.
So thank you very much, Veit. Very welcome from my side. My name is Dominik Katholnig. I'm working in the engineering department at Rotax, and I will give you now an overview about the H3PS, or a first overview of the H3PS project, and especially the Rotax part within this project. So what does H3PS mean? H3PS is actually quite a tongue twister, but it is an acronym for High Power, High Scalability Aircraft Hybrid Powertrain, and as was already mentioned before, this is a European Union project within the European Union Horizon 2020 Research and Innovation Program. So what you can see here on this slide is again the H3PS acronym. It is a project that is 100% financed by the European Union, that was already mentioned before. But now the interesting thing, the project objectives. What were the project objectives? So it was to develop, to manufacture, to test, and finally also to fly a parallel hybrid powertrain system for general aviation. And we wanted to show demonstrate the challenging advantages of this concept, but also the scalability level. The partners were, as already mentioned, Tecnam as the aircraft manufacturer, then Rolls-Royce as the electric system provider, and we, Rotax, as the internal combustion contributor. On this slide, you can see part of the system architecture. How does that look like? So on the very right side, you can see the propeller. The propeller is driven by the Rotax propeller shaft coming out from the Rotax gearbox. So our engine, the 915 IS, does also incorporate this gearbox. And on the left side, you can see the electric system from Rolls-Royce. The electric motor is linked to the internal combustion engine via a mechanical coupling element. And so the power is transferred from the electrical machine to the internal combustion engine, and then via the gearbox to the propeller. About the left side, I will not talk about that anymore, because I will give that to my colleagues from Rolls-Royce afterwards. Here in these pictures, you can see where the engine, where our 915 IS engine is placed under the cowling. And now I come to the mission profile. So our Rotax 915 IS engine delivers 104 kilowatt of max takeoff power and 99 kilowatt of max continuous power. And in addition to that, so in addition to the 104 kilowatt max takeoff power from our engine, we have 30 kilowatts for 1 minute from the electric booster and another 25 kilowatts for 5 minutes afterwards. And so we boost the takeoff and the climb, or the initial climb, and then afterwards we go to a recharging phase of 25 minutes. Now I will come to the 915 IS engine, because as I said, I want to focus on our part of this project. So what is this engine? It's a 4-cylinder, 4-stroke horizontally opposed internal combustion engine with a turbocharger. You can see the turbocharger at the bottom of the engine. With this turbocharger we have a critical altitude of 15,000 feet. It's air and liquid cooled, so the cylinder heads are liquid cooled, other parts are air cooled. And what you can also see here in the picture is the gearbox. The very right side of the engine, you see the propeller shaft and then the gearbox in black. And with this gearbox, we reduce the engine RPM with a ratio of 2.54 to 1 to the propeller. So if we have a max engine RPM of 5,800 RPM, we then have a propeller RPM of about 2,300 RPM. About the performance data, as already mentioned before, we have 104 kilowatt max takeoff power for 5 minutes, and then we have 99 kilowatt max continuous power, which is most of the time also climb power. With a weight of about 82 kilogram, we have a quite impressive high power to weight ratio of about 1.3 kilowatt per kilogram. And with this engine, you can fly up to an altitude of 23,000 feet, which covers actually most of the VFR flight envelope. About the geometrical data, we have a bore of 84 millimeters, a stroke of 61 millimeters, and with this we get a displacement of about 1.3 liters, and a compression ratio about 8.2 to 1. Some nice to know data about the system. In the gearbox, we do not only transmit the torque, the RPM, but we also have a mechanical shock absorber which absorbs the torsional vibrations, and we also have an overload clutch. So in case if the propeller, for example, should strike the ground or something else, the engine is saved by this overload clutch, which decouples the engine from the propeller. We have a dry sump forced lubrication system with a separate oil tank. This is not shown here in the picture, but what is shown here is, of course, the propeller shaft. And when it comes to propeller, we can have a fixed pitch or a constant speed propeller. For H3PS, we used constant speed because, of course, if you use constant speed propeller, you're more efficient over various speeds. We also have the possibility with the 915 engine to supply a 20 volt board system. With the 915 ISA engine we have 12 volt. So this is also what we have used in H3PS. Our 915 engine is a smart, is a safe, is a clean and future-oriented engine. Why? Because in the electric system or in the management system, we are fully redundant. So we have fully redundant actuators, we have redundant sensors. We also have, as a kind of brain, also a fully redundant ECU with 2 channels, lane A and lane B. And also when it comes to ignition and fuel injection, we are redundant. We have a TBO of 1,200 hours, and when it comes to fuel efficiency, we are also good with 325 gram per kilowatt hour at 5,800 RPM. So this is at max takeoff power at ESA sea level. And we also have a lean mode, what is called lean mode, eco mode. In this eco mode, we lean the engine, and then we come down to about 265 gram per kilowatt hour. We normally operate our engines with MOGAS, not with leaded avgas, and that is also, of course, good for our environment. And this is why we consider our engine, our 915 engine, at the moment one of the best engines on the market. And these are also the reasons why this engine was used for the parallel hybrid system, because you need to rely on not only a safe system, but of course also an efficient system. Now I come to the work packages in the timeline. What you can see here at the bottom is the timeline. You can see that the H3PS project started already a while ago in 2018, and it now ends here in March 2022. There were several work packages where Rotax had the lead in work package 2 and work package 5. Especially work package 5 was quite a challenge for us, because we had to test the engine. That means not only the Rotax internal combustion engine, but the whole propulsion unit. And I will come to that now. Because when I'm talking about the main tasks, as I said, we provided the combustion engine, which was slightly adapted for H3PS, but the main part actually from our side was the technical supporting and the testing. We did 150 hours endurance run, for example, to see how the system is behaving in different phases and with the mission profile intended. And here we already saw where the weak points of the system are and which things we had to change. Finally, we also did, and this was done on the dyno. And afterwards, or before handing the engine over, the propulsion system handing over to Tecnam, we did a 5 hours audit run to verify that everything is working properly. And we did this 5 hours endurance run then on the propeller test bench at the aerodrome in Wels. What helped us also was or is the fact that we have a machining shop quite close to the dyno at our site in Gunskirchen, and so it was possible for us that we could easily change some parts. And we also, of course, profited from our knowledge from reference aircraft from other installations, and we could hand over this knowledge to the hybrid installation. And of course, we have other projects and powertrain developments running, and we could also benefit from that. What you can see here is the connection of the ICE, of the internal combustion engine, with the genset. So on the left side in blue, our Rotax 915 engine. And I highlighted, or I want to focus on this picture a bit, because during the test runs, we saw that this part, the big black part, this is the rubber coupling element that connects the two propulsion systems, that this part is really highly stressed, and we had to really focus on this part when it comes to stress, when it comes to torsional vibration, and also when it comes to temperature. So finally, to conclude, what can we say about this project from Rotax point of view? We can say that the project objections or the expectations were met. We gained a lot of knowledge, especially in the overall system design, but also, of course, in seeing how the different systems work together in the interaction of the systems. And with this project, we had the opportunity to develop a new concept and to show how it works with a conservative approach, because we had a completely new propulsion system, a hybrid propulsion system, but we had a major aircraft, so a major environment, and also, of course, our 915 IS engine is a major serial engine, which helped us to avert a lot of risk in the project. We see H3PS as an important step in the hybridization of general aviation, because we also saw how important it is to have good partners in such a project, and we of course want to focus on that and strengthen our relationships in the future. It gave us also the project also gave us the opportunity to share our experience, but most of all with 915 IS we once saw again that this engine is really reliable, it's fuel efficient, and it can not only be used in conventional aircraft design but also in hybrid systems. For the future, there are still many challenges. As you said before, probably 5% of the way. A lot of work to do to reach maturity of these systems, but if we further strengthen our relationships, if we work together, if we really try hard, I think it's makeable. And of course, all those system concepts have to be evaluated. We're currently doing that. And the goal is, of course, to become quieter, to become cleaner, and have less fuel consumption. But want to make sure that Rotax is really pushing forward greener and cleaner aviation, and we really have that in our mind. So thank you for your attention, and we're open to questions now.
I know that our Rotax colleague have a very tight schedule, so I think if there are some questions from the audience, or I don't know if we can have questions from the people which are not in this room today, I think they can spend other 10 minutes with us for maybe answering some question. First of all, I'd like to thank you for presenting Rotax, and it was a very nice overview of the company. And thanks for the short but effective, efficient summary of the project. And maybe I can start with just to give opportunity with one simple question. What about from pilot perspective using hybrid propulsion? Is that more is reducing the pilot workload, or maybe increasing, or opening other problems?
Yes, maybe our colleagues from Tecnam can answer this question better, especially your test pilot. But
it's a good question, but I think we are in a too early stage that pilots are really thinking about which kind of alternative propulsions they want to choose in the future. There are many hypes in the moment about e-propulsion, about a hybrid, about range extender. We have a lot of topics in our company on the table, but all are in a very early stage, and pilots, you know, everybody who is long in the aviation or is a pilot by itself, the aviation is the development processes takes longer, and everybody has a little bit more conservative attitude. So we have not a really knowledge in the moment where we can say pilots ask for that or for that.
I just want to add something about the pilot workload, because with this aircraft, where the primary objective was not to make the pilot workload easier, but just to demonstrate, as Veit was telling, the system. I can tell you the very last flight that we made. So we made last flight with the 2 aircraft. Lorenzo, our test pilot, with the hybrid, and myself with the standard P2010. And it was very, very strong wind, crosswind. And once we landed, he told me I was so focused on the 2 engines management that when we take off, I forgot to fly the aircraft. So in this stage, we really focused on the engine itself.
Yes, maybe the study on the pilot workload is in the 95% pathway. Okay.
So Nello Cozzolino from Piaggio. Thank you for your presentation. We know that Rotax is a solid position in the engine for general aviation. But what about the future? I see that you already started test the engine with sustainable aviation fuel or synthetic fuel, whatever will be we call it. Is it your future way to see this engine burning more sustainable fuel even more? What could be the problem? Because I know that the impact, all of us discussing in Europe, we know that the general aviation is not doing a big impact on, but still the customer has to have some need to fly in a sustainable way. So do you have any plan to do this research on that?
Yes, of course we have a plan. But to the status of now, we cannot say we are going that direction or we are expecting that. But we are sorting out all possibilities to get an improvement, to get greener, and they are completely different kind of maybe future goals or solutions. But we are still in a period where we watching on all topics and very seriously. We are involved in many different projects as well. And as soon as we have something news from, really definitely news from Rotax side, then we just let you know it.
Good morning, Fabrizio Nicolosi from University of Naples. My question is on the, let's say, the combustion engine. You are, let's say, as a Rotax leader in the lower power class of this engine, like below 160 horsepower. But for the higher level, like 300 horsepower, which will, I think is also a very, let's say, larger market for the general aviation aircraft. Do you think that it should be time to develop new engine? Because basically the engines that are used are the Lycoming, which have a very high specific fuel consumption, and also using a, let's say, gearbox, which maybe is, they don't use gearbox, sorry, and this could be an advantage for the fuel consumption. And so what is your perspective as Rotax? Are you going to jump in this market, or you will stay below this level?
It's a good question, and we are always thinking about where we are going. We are coming from the low horsepower sector, and we already raised the last 8 years around 40 horsepower more with the 915. and with the 914 was 115 PS or horsepower. The 100 horsepower engine are the most sold ones. But that depends on very many different aspects to go in the higher classes. The markets are completely different to the market structure of the lower horsepowers. If we are going inside, everybody knows there are some big other competitors. So the strategy to enter into this market has to be completely different to that what we are doing since 4 decades. And that is the reason why we not decided yet what we are doing or what will be the future. When we are going in that direction, I unfortunately cannot give a more concrete answer today, then we must be really convinced that that product that we are offering in that market can compete with others very good, because then we are in a completely other structure than we are now with this kind of horsepowers. And in the moment I have any news that we would have a product in place already and that we can start with success into this market.
Any more questions or maybe curiosities? But do you manufacture engines with high horsepower? I mean, for other application, not aerospace. No.
Also recreational vehicles are not more horsepower than in the aircrafts.
And can you tell us how much of your business is aerospace and how much is outside or aerospace? Maybe ski or...
So you're thinking about the completely BRP concern?
Yeah.
We are a small part in that.
Yeah. Okay. But it was just for completing the Rotax presentation.
No, it's okay.
Yeah.
And we are a small group as well from aircraft. We are in total over the world with BRP around 7,000 employees. In Austria, where we are constructing the engines, we are 1,300, and the aircraft business is running with around 100 people.
Okay, thank you. So, if there are no more questions or curiosity, I would like to thank you again for coming and for your very nice and interesting presentation. Thanks a lot, really. And have a nice trip back. Well, it's now Rolls-Royce time. Okay, so please, Mr. Zoltan Koltai, representing Rolls-Royce here in the project. The podium is yours.
Thank you very much. I'm Zoltan Koltai. I'm head of manufacturing for Rolls-Royce Electrical. And I'm here talking to you because I provided management oversight for the HCPS project from Rolls-Royce side, as well as it's very nice to be here in Naples. So thank you very much for the opportunity. So I would like to tell you a story which took us from here, from the very beginning of the concept, to here, where actually we could fly the system successfully and safely. First, I would like to share with you about our propulsion system, the electrical part of the propulsion system, of this parallel hybrid system. I would like to talk a little bit about how could we achieve that and how modular is our system to serve various kind of configurations. I would like to share a couple of challenges we encountered and then opportunities out there for the future, which I think could exist in big numbers. First of all, about the HCPS project, I don't want to repeat what Daniel also shared before. This project, the Rolls-Royce part of this project was to provide the electrical part of the propulsion system, and the electrical part consists of the electrical motor generator starter in one unit, of the controls and the batteries for that, as well as the wiring, human machine interface, and the entire system control, both hardware and software in this project. When it comes to the project execution, we were part of a consortium, but we had our own work packages, which we had to deliver to contribute our fair share. I have to tell you that actually during the project, it did not feel like we owned one or the other work package because we worked so closely and even more closely as we progressed with the partner Tecnam and Rotax. Yet, a matter of fact, we had two work packages, the design and architecture of the regulatory framework studies, and then also the hardware manufacturing for the components of the electric propulsion system was our leadership in those work packages. So now a little bit about the electric propulsion system. It's a complicated diagram, I know, but I would like to break it down for you so that it's more digestible. On the left side, you see the propulsion system engine compartment from above. Whatever is reddish color, that's our contribution, Rolls-Royce's contribution to the system. And it becomes apparent right away. If you look at the figure, the battery pack obviously is a sizable one, but otherwise the electric propulsion system, all components are tiny compared to a conventional engine. And consider the Rotax engine in the picture is already smaller than a typical other competitor engine powering a similar aircraft. Now here, the parallel hybrid system which we have had in operation is starting from the right to the left on this diagram, starts with the propeller connected to the gear and the internal combustion engine. Then he had already explained how that connection works. And then we, with a flexible coupling, are coupled to the electric machine. I call it electric machine because it is a starter motor, it is a generator, and it is also a booster motor during takeoff. So it is serving three purposes in the same unit. This electric machine is now controlled and powered by the inverter, which consists of the power electronics and the controls, and providing the three-phase alternate current to the motor to operate. The inverter gets its command from the so-called vehicle control unit. It is a torque-controlled system, the inverter and the motor together, which means that the torque is the command which the inverter is receiving. The vehicle control unit is the one which is, I would say, the brain of the entire electrical part of the propulsion system. And this brain decides, based on the information received from the batteries, from the cockpit human-machine interface, for example, the thrust lever, all the information collected, and decides what command to send to various parts, for example, the inverter. The vehicle control unit, therefore, receives power command from the thrust controller, and then calculates what kind of torque is needed in order to have the right power on the shaft, controlling the torque eventually. Of course, for communication between the vehicle control unit and the cockpit control unit, we need to have that continuous information exchange, which eventually is displayed on the human-machine interface. And I would like to highlight another kind of sub-brain or subsystem of the system, which is the battery system master. That is the one which is providing the energy to the inverter, the direct current energy, as well as managing the battery modules and the safety considerations there. It has contactors, so unless the pilot commands the contactors to engage, there will be no energy flowing into the inverter. And vice versa, if the pilot commands or it's automatically shutting down because of, for example, a short circuit, then the contactors are disconnected. I have to also mention that we have power supply unit, which is for redundancy. And that power supply unit practically makes sure that either through the auxiliary battery or the main battery, the system always have power to operate because it's essential in aviation applications to always have the system powered. Now, you may also observe that here we have the motor and the inverter, both water-cooled, actually liquid-cooled, and on the same cooling circuit. So it was very important for us to figure out how can we actually manage the cooling appropriately for these two systems. There were some other things which we did not appreciate at first, and then I will tell you that about those during the challenges section. A couple of words about the motor. The motor itself is a alternate current synchronous motor, sensorless motor, so it's different than the automotive industry typical applications. The other way it is different from the automotive applications is that it is a higher power-to-weight ratio. It's nearly 3 kilowatt per kilogram in power-to-weight ratio. And also, to achieve that kind of lightness and powerfulness, we had to design a different kind of machine than what you can find in, for example, an Audi or a Jaguar. And the difference is that this is a radial flux machine with surface-mounted magnets, with composite magnet retention, while the automotive engines are mostly internally mounted magnet machines, which is less in power-to-weight ratio, but obviously much easier to manufacture and design. The stator is concentrated winding stator, and this is a liquid cooled through its cooling jacket, so it's not directly but indirectly cooled. And we found that it was very sufficient for all kinds of circumstances. So the idea that we cool the motor so indirect way was proven during this project as well as some other experiments we had before. You already by now probably read the data, so I won't read it out loud. So I will move to the next slide, which illustrates how it looks like in real life. What you can see in the top left is the coupling element coming out of the internal combustion engine, and this is where the motor is actually connected. The motor itself, you can see on the top right, before being connected, with liquid cooling inlets and outlet on the right side, and then the three-phase alternate current connections on the left side. In its assembled state, but still not installed into the aircraft, that's illustrated in the bottom left corner, and then eventually a close-up after the installation with the internal combustion engine. The batteries was another specific challenge. The battery actually just serves two purposes again. It is providing the boost energy during the takeoff of the flying. It also provides a energy storage possibility during cruise when the aircraft is charging back the energy into the batteries. So that's pretty much a buffer. This is air-cooled. Another challenge during the project was how to manage this air cooling in a way that it is continuously sustained. We made lots of simulations and lots of testing in laboratory to figure out what kind of cooling do we need, what airflow, what happens when the temperature is rising. And actually, it was quite fulfilling that we saw that during flight, with the help of Tecnam and their expertise in managing the airflow, it was very well achieved, and we had no issues with the battery temperatures due to overheating. A couple of words about the modular system concept I think is a good idea here. So this was not the first time we were engaged in a hybrid system. There is a so-called serial hybrid system, which is not working with the electric machine and the internal combustion engine on one shaft rotating the same RPM, but they are decoupled. And the serial hybrid system practically works in a way where there is an electric machine connected to the propeller shaft, but then the energy is coming from a generator set elsewhere located. This enables a very good opportunity for the distributed propulsion. So that's one of the potential outcomes of the project. As you can see, this aircraft is a real installation, and this has been flying as well. So we have that experience under our belt, but this is very different in nature than the parallel hybrid system. So we could carry out some things, like for example, the architecture and the architecture components. We could not carry out the exact setup, carry over the exact setup into this project, so there was lots of learning happening in this H3PS project. The same aircraft, the Magnus E-Fusion aircraft, was installed with a full electric system, and it is actually very interesting that the same component, many of the same components we could use in a different configuration for this system. I have to mention that there were other aircrafts, just to mention one here, the flight design aircraft, which was also using, again, the same electric propulsion, full electric propulsion. So how is it possible that we have the same architecture for very different platforms and very different configurations. The way we could manage that, because those logics and those hardware and those software which we are using, they were evolved consciously in a way that they would be flexible. So first we started with a full electric battery system, and there we did not have any redundancies for the battery energy provided. We had that in the top left corner, and from there, consciously in mind with potential future hybrid applications, we created redundancy for our battery systems. So now on the bottom left, you can see two strands of batteries, and then if one is taken out, the other can still provide power. It was a logical next step that we took out one of the battery energy sources and replaced it with a generator set, because the inverter doesn't care where the energy is coming from, battery or generator set, it is just electrons. So we could actually replace with the same system architecture and components, replace the battery, one of the battery strands with generator set. Eventually, we could reconfigure the same system based on the experiences and have a parallel hybrid system. Of course, it was lots of work. It's 4 years of hard work, but still we did not have to start from scratch. So the challenges, which also Daniel before me mentioned, was numerous, but one of the challenges I would like to highlight is, interestingly, the interface in between the internal combustion engine and the electric motor or the electric machine. This is almost funny that right at the connection of the two systems, the two worlds, that's where we had one of the major headaches. And the headaches were that it's not just mechanically challenged, but also both the transients and the constant temperature thermal load on the coupling was very challenging, as well as the polygon element connecting these systems. So what we had to do is we had to reinforce and change the material for the coupling element, the polygon, which you can see on the right side. And regarding the rubber, we had to introduce additional cooling with the help of our good friends at Rotax and Tecnam, right into the heart and the middle of this entire hybrid propulsion systems, and then continuously cool it during flight, and then we could achieve a stabilized temperature. That is something which was a very interesting learning, because this was the least anticipated as a problem, and this caused us almost the most headache during the project, but we solved it because of the great engineers on this job. Opportunities are obvious, and there are some non-obvious opportunities. So one obvious opportunity is that we have announced a collaboration with Tecnam around the P-Volt aircraft, which is carrying over lots of learnings from this hybrid system. As I mentioned how flexible the architecture is, so I think that learning is even though this is a full electric aircraft, but very well to be carried over into this full electric commuter aircraft. The non-obvious learning or opportunity really is actually it was an understanding for me during the project. I remember a situation where we were standing in the hangar trying to educate the test pilot Lorenzo De Stefano around how to operate the system. And we had very good description in advance about how the Royce system works. We had very good description about the Rotax system, and we gave it to the pilot and walked them through. And then during the walkthrough, when Rotax explained how the system starts up, we said, like, wait a minute, if you do that, our system will not get the right communication. So we started our part, we explained how our system starts up, and Rotax colleagues said, like, wait a minute, that's not possible, because then our system will stop. And, all this was, you may say, how is it not obvious when we started to work together? Well, we had to be there, we had to start doing it in physical environment. And then we spent the rest of the evening and most of the night, by the way, in the meeting room, going through step by step. And instead of, a checklist like this, we ended up with a checklist like this. And I think that's a good metaphor for how we have to collaborate in the future with anyone, including Tecnam, of course, and including other partners. This is the way hybrid systems and any system can come together. This is, for me, was a great understanding, and I will keep telling this story to our colleagues so to improve our way of cooperation. But I would like to also share it with you. Thank you very much for your attention.
Facciamo la mouse. Okay. So again, if there are some questions or curiosities, thanks for the also telling us the real word, and this is I think the essence of a multidisciplinary approach. That is another thing. I mean, aircraft is obviously a multidisciplinary, let's say, discipline, but practicing, because this involves also the attitude of the people involved in the, and that's quite important. Yes, I know. But okay, we have one question from Professor Del Pizzo.
I'm Del Pizzo from University of Naples. I would like ask you some additional information about the motor. You say electric motor. Is a permanent magnet motor, axial flux, or traditional, or not, and the winding is traditional or hairpin, and more the frequency, the switching frequency, and also basic frequency from inverter. What are the values, and number of poles of stator and rotor are equal?
Yeah. So this is a permanent magnetic surface-mounted magnet rotor motor with concentrated winding, concentrated copper round wires. And the motor itself is operating with a alternate current without sensor, so that we are deducting the information about the RPM, for example, from the signal of the voltage and the current detected in the motor. And that's one of the indication why, like, 1 RPM or similar very low rotation is not manageable with such kind of motor. So it's one of the reasons it is different from a typical like automotive application. The switching frequency of the inverter, I don't know by heart, and I have to. I don't want to give you a wrong information. The control, the inverter is controlling 3 phases. So it's not a redundant, but direct 3 phases into the coils. And there are 3 coil connections, 3 joinings for those 3 phases from the motor.
Some other information, the switching devices are traditional or in silicon carbide.
Yeah.
And another thing, you say the rated power is 30 kilowatts. You say rated in the electrical sense for continuous work, because this booster is used only in takeoff operation. And why you select a motor who has the rated power, but it works for only few minutes at that power?
Yeah. So the motor is capable of continuous operation at 25 kilowatt, and that is something which calculated during the mission profile assumptions. So that we choose, that's why we choose that kind of motor. The motor is capable of running at higher torque and higher power. At 32 kilowatt actually is what we measured in testing. But that is something which we did not want it to stretch further. It is possible, very easily scalable, to have a higher power for very similar or even better power to weight ratio. That was not demanded during the project because not of the motor capabilities, but we had to be considerate of the weight of the batteries. And in order to provide the right power of the batteries, we already had to have a very sizable battery on the 5 volt So that was the limitation mostly than the motor. The inverter is conventional silicon, but then we also acknowledge that the future developments are definitely going towards silicon carbide, no question. Thank you.
Thank you for your presentation. I have just a question about the scalability of the solution. Do you think that the link between the engine and the electrical part, the combustion engine, will be, as the rubber one, will be scalable at a larger scale, or it is just because you have a couple an alternative engine with the electrical motor, but if you have, for example, a turbine engine, this type of couple would not be the same?
This coupling will not be the same. We have a project actually with the so-called new small engine, which is a miniaturized gas turbine. That project has started, and we are hoping to develop that in the next few years into a product. That is coupled with not this, but a newly designed generator, which we will put together. Very different RPM, definitely silicon carbide controlled. But that is something which was a very good learning for us from this experience, that we cannot use this kind of coupling in the future, especially for that gas turbine coupling.
Let's see if there are... Yes.
Good morning, I'm Andrea Marotta from ANAC, Italian Civil Aviation Authority. I'm Director of Environment and Aviation Sustainability. First of all, thanks to Tecnam for this project. Thanks also to the organization for this important event. We're really interested in this kind of events. I'm here to show this interest because we are working on a new regulation about refuel. So perhaps this is one of the steps to be taken in this field, in general aviation, of the pathways, as the Professor Dominik said, this pathway towards new frontier. Also because also our time as our Earth is not an exhaustible resource. Therefore, we must move on as soon as possible. We do know it. So perhaps it's not a kind of question, it's just the kind of approach that Rolls-Royce has got right now towards the sustainable aviation fuels. I mean, this shows how Rolls-Royce is interested in developing something new as an electrical resource for the engine. At the same time, now in the short period, we're really interested in know what is the stakeholder and enterprise industry approach toward the new sustainable aviation fuels, which means just one of those basket of measures which are in the ICAO indication and guidelines, but are right now possible to achieve and to use. Therefore, what is exactly your approach towards SAF as Rolls-Royce? We know already that Rolls-Royce have developed a kind of new engine with old SAF, but we would like to know, just to know, also because it could help our work together with the other authorities and member states. Thanks a lot.
Yeah, thank you. That's a very good comment, and I fully agree with you. What Rolls-Royce is doing is looking at the carbon emissions and carbon footprint holistically. So this is a big equation, including electrification of the propulsion, which is one obvious, very direct contribution. Also, the so-called more electric aircraft, especially in large civil engines and larger aircrafts, that's definitely happening as well. And there is lots of opportunities in developing into more electric power into the aircrafts. Then beyond that, also sustainable aviation fuel is something we are committed to. Every new development we are doing in the gas turbine area, including the new small engine to be coupled with our new generator, is enabled for that, for sure. And then beyond that, we also have the so-called small modular reactor, which is not just decreasing the consumption, but also providing clean way of generating the energy. And that is something which, as a big equation together, is then really having an impact on the world. I have to also mention that with our development in the battery storage area, which is probably the toughest challenge for the entire electrification of aviation, we are considering not just about how to have the batteries there for the aircraft, but then also what happens after they reach, say, 80% of their capacity. They have to put them somewhere, and we cannot just put them into a landfill. So Rolls-Royce have Rolls-Royce Power Systems, and obviously other partners potentially, who can actually utilize them in standstill ground operation to stabilize the grid which is another big problem for our world. Not just don't have energy, but don't have energy the right time and the right place. And this grid stabilization would really contribute. Right, right. So that all contributes as a big equation into sustainability of the emissions as well as the power grid. Thank you.
Okay, let's see if there are, yes, thanks.
Hello, Michael Lenton from Leonardo. I was looking at the objectives of this project, and firstly, let me compliment you and the team on achieving what you did achieve during the pandemic period, because we know how it's affected a lot of the industry, and in terms of productivity especially. Just looking at the objectives of the project, was the element of safety for the aircraft one of the concerns, one of the objectives in terms of what instinctively comes to mind as a pilot is extending the glide range in case of combustion engine failure, and in the case of applications for drones, extending the glide range of the drone in case of combustion engine failure or other failures as well. Was that a consideration in that? And how does that impact the idea of the coupling between the electrical element and the combustion engine drivetrain?
Absolutely. That was the number one kind of importance for us, because what's point in having a technical success if someone gets hurt or a property gets hurt? So absolutely, that was number one. To step back, I would say that on the journey of getting from an idea to a product, like 0 to 1% is having a demonstrator in the laboratory. 1% to 10% is to make it fly. So it's 10 times more effort. No matter how good results we have in a laboratory, I tell it to you from experience, if you fly it, then it's a completely different mindset and completely different activities. Then from a first flight demonstrator to product, that's another 90% of work to be done. So in that big picture, yes, that 9% delta between the laboratory demonstrator and the flight prototype is really mostly about safety. And what we've done is obviously the usual things, hazard risk index and failure hazard analysis, and all those right stuff were in place. And then we communicated very closely with Tecnam, with various departments of Tecnam, to understand what is the risk propagated into the platform, into flight operations from the propulsion system. So I think, again, beyond the right tools to be used from safety point of view, actually the right communication and interaction and trust was very important in between parties. And not to delegate problems to others, just to help each other to solve the problem, because then we could secure that nothing falls into the gaps. So technically, that also meant that we had to consider things like, do we have an additional starter motor generator, a starter, instead of only having one motor generator and starter. That actually was the case. We had an additional starter as a backup. Also, we set up the system in a way that even if we have a complete seizure of the shaft with the electric machine, still we measured and calculated the torque resulted from that, and calculated and simulated, and then later also experienced what would be the power available during takeoff, even if the worst happens and there is a complete seizure of the electric machine, like the rotor touches the stator. And we found, and only after that we proceeded into the flight campaign, that even with that we could provide enough climb power for way higher than 500 feet per minute climb. Those considerations were baked into the design of the system and the coupling, and then were part of our hazard risk index. Did I answer the question? There is a long story, and I can tell lots of experiences about that, but I have to be concise as well.
Some more additional questions or comments? Well, I would like to thank you very much for your presentation and for answering the questions from the audience so precisely and so at the right point. Thanks a lot, really. I think it's been a very, very interesting dialogue between the speaker and the audience. Sure. And well, now we have the most important part of the day, which is coffee break. And but the very good part is when coffee break is short. That's better. Okay, so it will taste better. So 11:15, we are back here. Okay, thank you. So welcome back, and thanks for being exactly on time. So we will maintain the schedule, which is important in events like this. And now, last but not least, obviously, we have Tecnam presentation. Tecnam presentation will be given by Fabio Russo. As I said at the beginning, Fabio is a very, very close friend. And I know that he will give us a multidisciplinary approach, an overview, an important overview highlighting, let's say, advantages and drawbacks of these new ideas on the propulsion, on the aircraft propulsion, not only on the hybrid, but having a wider overview on the actual research path. Fabio is he's a pilot, which is something that it's very nice. He is also the research responsible for Tecnam, and these are the lowest activities of Fabio because he does many other things. And in this context, I am asking Fabio to give his lecture in Italian because of the site, because I know that there are some students linked over the network, over the YouTube, and I will prefer, since I know part of your presentation, or at least I know, I am not sure, maybe you changed everything. And since I think he may be also a sort of aircraft design lesson, I asked Fabio to give his presentation in Italian. So I switched myself in Italian. And I'm sorry for you, but yes, you can wear your headphone, and you have your simultaneous translation. Quindi, come dicevo, ho chiesto a Fabio di fare la presentazione in italiano.
To present in Italian, because I want to specify, that, as a pilot, he can perfectly speak English. So I asked him to speak Italian because I want his lecture to be understood also by Italian students. Actually, I could read some notes, his presentation in advance, and I do think this presentation can be a lesson, actually a lesson. I also thought of inviting him to my classroom, because I wanted him to speak to my students. So I asked him to speak Italian. I apologize with our foreign guests, but so here we go, Fabio Russo. Yeah, I have to lower my microphone, unfortunately. Thank you, Professor Marulo. We're all, acquainted with one another. My name is Fabio Russo. In Tecnam, I'm in charge of the R&D department. I've been working with Tecnam for 17 years now, and this is the funniest department of the company. It is the place where you see the aircraft being born. You have less paperwork to deal with. You grow every day. You see the project being born and grow on a daily basis, and until you can give it to the end customer. But even beyond, because an aircraft doesn't end there. You know, once you give it to the end customer, another journey begins because there is a continuous improvement process, continuous modifications of the configurations, new optional accessories. New technology allows us to find new solutions for our clients. Today, you know, we are here to celebrate our H3PS project. It's a unique project. It is the first time that a hybrid parallel propeller, the IC and the electric motor are joined and generate together the power for the aircraft. It is the first time, it's really the first time this is done for a GA aircraft, a four-seat aircraft in our case. Let me answer to your question why that power was chosen. You know, there are several reasons, apart from those that Zoltan has specified. You know, the reason number one is to have a configuration that, by weight of the whole propulsive system and power, is comparable to the one that we are already manufacturing and deliver to our customers. This propulsion system has the same weight, the same mass, batteries included, as the configuration with the Lycoming, 30 kilowatts, because coupled with the Rotax 140 horsepower, so we can have the takeoff power, exactly the same takeoff power as the Lycoming. So we are here to celebrate the project, but the title goes beyond. You know, it is a pathway toward sustainable general aviation. So the title of this event is a pathway, is a journey, and the title of my presentation is In Search of Sustainability. It has to do with an aspiration. It is like you know, a search, a quest for sustainability. Why did I choose this title? The title that I chose represents all that is going on, that has been going on for a while in the GA sector, in the GA industry, in the whole world, all over the world. There are new players entering the market, the VTOL, the vertical takeoff aircraft for urban air mobility. In history, in the history of aviation, this is a very special moment, you know. In my opinion, it is extremely important that we pay attention to what is feasible, what is realistic, and the real potentials of an electric aircraft and a vertical takeoff electric vehicle aircraft. Sorry. So for this reason, I thought of developing the Breguet equation, the Breguet range equation. It is the formula to calculate the range of conventional aircraft for electric aircraft, just to find a straightforward tool to critically assess the news, the million news that we read on the net, on the social media. There are lots of announcements of projects, you know, and very rapidly we can assess a press release, even if we do not know the aircraft that is being presented, you know, with the Breguet formula or Breguet equation, this is a slide, then I also have a slide to answer one of the questions that was asked. Why, if an electric car has 400 kilometers range, why shouldn't a full electric aircraft shouldn't? And then show conclusion. So let's start from the beginning. We are overwhelmed with news, fake news on the social media. We have these tags, the hashtags, advanced air mobility, urban air mobility, and electric vehicles or aircraft with vertical takeoff, conventional takeoff, or landing takeoff, conventional, etc. Different tags. There is a need for sustainability, and we are all committed to reach this goal. But in this period, there are also other needs. Investors, financial investors, new players are being listed on the stock exchange. So also the world of finance is involved. And we should also sometimes analyze the releases, the press releases that are circulating on the different channels. Unfortunately, in many cases, they are not realistic, and in 2 years' time, we'll have to realize it. Nowadays, from now, with a simple render, with a scale prototype, you can even get to listed companies. So there is no product. A render is enough to get to a listed company. And we see it with companies that are created ad hoc to be listed. We see projects, renders, or prototypes, that get to the stock exchange. There are lots of promises that then are, not always kept. And that is why there are two risks. Risk number one, there is, the risk of the speculation bubble. It would be the first case in the GA industry. And risk number two, and as an engineer and as a lover of aviation, this is very important. We as engineers, as professionals, as entrepreneurs in the aerospace industry, we lose our credibility when investors who hope to have a return of investment in 2 years' time then realize that it doesn't happen. If not always, at least often, it doesn't happen. That is why for our industry to remain credible, we need transparency. In order to stay credible, every company, every engineer who reads a press release should be critical in interpreting announcements, news. Also, the timelines are sometimes too fanciful, and we should also be very critical in terms of specifications, technical specifications, performances, emissions. So we shouldn't forget that a car and an aircraft, whether electric or fully electric, is not zero emission. Not only because there is an energy mix, but because in order to make kilowatt hours of battery for the next 20 years, for every battery kilowatt hours, you emit 73 kilograms of CO2 and then 4 kilograms of CO2 to transport the battery to the factory where it is needed. So you should be very careful. You should think twice before saying zero emissions. And you should also consider costs, running costs. In the press releases talking about future aircrafts, I read that the running costs will be far lower than conventional aircraft. It's a risky business, you know, and because buying an aeronautic battery, a battery for an aircraft nowadays and in the next 10 years, you know, because the scale economies in the aircraft industry do not happen like in the car manufacturing industry, and it costs $1,200, $1,500. So P-Volt, an aircraft like P-Volt, has a battery that costs $250,000, 230,000 euros. You may say that you buy it once and then you recharge it. Not at all, because the life cycle of a battery nowadays is 700, 800 cycles before passing from 100% of storage capacity to 90%, and below 90%, no aeronautic application is possible. That's the end of life, you know, of a battery in our industry. So 230,000 euros for a battery divided for less than 1,000 flights means a huge share of the direct running costs. And then the news. The era we live in is the era of the forward-looking statements, sort of disclaimers that the new players in the urban air mobility industry listed on the stock exchange add at the end of every press release. I'll show you something that is not confidential. It is something that you can easily find online to let you understand how important it is to critically analyze every press release, every line published on LinkedIn, on Facebook, etc. So this is the news. This is the piece of news 2 weeks ago. NetJets agrees to purchase a Lilium Zoll electric air taxi, 150 aircrafts. A person says, okay, they purchased the 150 aircrafts. They gave a lump sum, an account, you know, they paid something. There was a commercial negotiation or transaction. Then, if you go into deep, you read this. NetJets will have right to purchase up to 150 aircrafts. It means that the client has the right to buy up to 150 aircraft. So I said, well, as a European citizen or as a world citizen, I have a right of buying a 787. Nobody will prevent me from doing it. I wouldn't do it because I couldn't afford it, but as a citizen, I have the right to do it. Of course, I'm not going to do it, but, you know. So then you get to the forward-looking statement and you can read these sentences. All that you have read so far may not happen. Why? Because there might be problems of inability to achieve anticipated specifications, or because the technologies that we are talking about might be unavailable or not certified for passenger use. And at the very end, the last bit, you are cautioned not to put undue reliance on forward-looking statements. So what I've told you doesn't mean anything. So It's only an announcement. We needed it, but you know, don't believe it. So you have to be very careful. Every time you read a piece of news, you have to be careful because we can be misled. It's misleading, you know, and we lose our credibility as engineers. And also, I mean, we lose in credibility in terms of representatives and professionals of the GA industry. This is an example that I want to share. Nowadays, what is the truth for electric general aviation? Designing, manufacturing, and certifying an electric aircraft is possible nowadays in terms of technologies, in terms of manufacturing techniques. So this is feasible. You can have it certified. You can commercialize it. This is feasible. So if you define realistic boundaries for what an electric aircraft can do, if you find customers who are ready to give up the dreams of electric aircraft with a range of 800 kilometers, then full electric aircraft can be a reality, I mean, even today or in 2 years. And easiest way to show it, Professor Fabrizio Nicolosi and all of you, I mean, will recognize it, is the Breguet range equation. It's a tool to calculate the range of an aircraft. It is an accurate tool, but it is optimistic because not because it is an approximation, but because it doesn't consider that before cruise speed, the aircraft must take off and climb. There is the roll on the airplane, the air conditioning is on for the passengers, de-icing may be necessary, so all the avionics must be switched on. It is optimistic for a typical range of an electric aircraft. It is 85 to 90% optimistic. This formula, if you take every bit of the demonstration, can immediately be transferred into a full electric Breguet range equation. You know, you can use it for a fully electric aircraft. Don't be scared. It's only, you know, a multiplication, you know, of bits. Look at this formulation. You know, in this, the aircraft is involved here and here. For the other bits in the hangar, you know, you can assess the contributions of the factors who will limit the range of the aircraft. So regardless of the weight, regardless of the design of the aircraft, everything that falls here and here has nothing to do with the aircraft that we are there to assess. Let's start from here. Rolls-Royce can teach us, because they are the leaders, you know, in the world. You know, they have shown it, you know, 2 months ago. They showed it 2 months ago with the world record of the fastest electric vehicle in the world. So at Rolls-Royce, they teach us that nowadays the technology exists, you know. It's the top, you know. Nothing is left to invent, I mean, to be invented. That it is a sensational technology. It exists, you know, it's a fact. Good performance, I mean, electric vehicles, you know, there's a performance of 95%. You know, it's huge as compared to an internal combustion engine. So the electric motor is not a problem for an electric aircraft. And the inverter is not a problem. The efficiency is 98% nowadays. Depth of discharge. This is the parameter that tells us what is the fraction of the battery that you will use during a flight? Starting from 100% battery and completing the mission at 0% means using up the whole battery. I have written 1. So, you know, I take off 100% battery and then when I land is 1%. Depth of discharge is 1 for the cars, you know. So, of course, with electric cars anyway, they suggest you not to go over 80% in recharging and not to go below 20%. So, you know, that's an abnormality. Anyway, let's assume we use up all the battery capacity. And then state of health, SOH, the fraction of the energy that the battery can provide to the aircraft. You can see your state of health on all your smartphones. If you read your smartphone, yesterday it was 86%, today it's 95%. So I bought this iPhone, this smartphone 13 months ago, and in 13 months the battery of my smartphone has lost, 15% of its storage capacity. And so when you specify the capacity of a battery, you know, when you give it to the end customer, I mean, needs that you specify that you will lose the capacity in a few months. You have to be honest with your end customers. Caver does 8 flights a day with one aircraft. So 800 flights in 100 days, in 3 months, you know. So why should we specify the range of the aircraft with the new battery when this range will diminish by 15% in 3 months? And then the performance of the propeller. 85% is a very good performance, but it's quite rare. You observe it very rarely. Also, the variable pitch propeller at constant revolutions are used at cruise speed. If the aircraft is designed to do the longest cruise possible, it means that it must be designed around the maximum efficiency speed. So considering 78% of efficiency of the propeller up to 85% is legitimate and realistic. So, has the aircraft anything to do with this? No, nothing. And this already tells you that whatever the aircraft, the range must be multiplied by 0.65 and divided by 0.71. So we have reduced the range by 30% even before seeing the aircraft. And then this is the second point. If I ask you, what is the density of the energy of a battery of a car? Can you give me an answer? Do you have an idea? 200? Perfect. 250 of the cell, you know, of course. And when 100 or 1,000 cells have to be put together in a battery pack, and this is necessary both in cars and aircraft, the weight of the pack increases. for the wirings and for the container, for the cooling, the ventilation, if, you know. So what happens? When this pack is assembled, you know, it goes down to 135 to 160 kilowatt hours. So nobody thinks that the energy density of an aircraft can be the same as that of a car. As an engineer, I have to work so that we can be close to that value and not to the other one. Otherwise, there wouldn't be any difference between car engineers and aircraft engineers. So an optimistic, a realistic, and feasible value is 210 watt-hours per kilogram. 210 watt-hours per every kilogram of battery. That was the one. So now let's start looking at the aircraft. These are some dots. Maybe you can see, no indications. You see, on the axis you have the empty weight, no battery, only the airframe, you know. On the y-axis we have the maximum takeoff weight. And then there are circles. These are all aircrafts of general aviation, and they are included within two curves, or 59 of the empty weight and 59% of the maximum takeoff weight, or 69. There are two abnormalities. Can you think of a GA aircraft, whether it is in composite materials, aluminum, turbo propellers, turbofan, whatever, old, new, any GA aircraft? Do you have a name, one? Not necessarily a Tecnam aircraft. Give me a name. Here it is. Here it is. The one you gave us. Even Piaggio P180, an excellent, one of the best GA aircrafts in Italy, falls within this ratios between empty weight and maximum takeoff weight. Two electric aircrafts. This one exists. This is real. Pipistrel Velis is likely outside this boundary, and also Pivot. Well, no, actually Pivot. Pivot also falls outside. These electric aircrafts have a lower weight than the others, slightly lower. But you'll agree with me that there's a problem there, you know. And if we continue like that and declaring that the empty weight of an aircraft is 29, we will have to understand that the buyers will have to be informed that they cannot transport 4,000 kilograms of batteries, but only 2,500. And so, I mean, the range will be lower. Do you want the names of those two? No, I'm not giving any names, okay. Unfortunately, we can't hear, I mean, the comments. One is in Wonderland, you know. This is the headline of an article that has been published today in this period. Anyway, and here this is another formula. So you have maximum takeoff weight minus empty weight minus payload rated, declared, etc. And in all these cases, you know, the fraction of the battery that you can put on board with respect to empty weight and maximum takeoff weight is this one, 0.29 or 0.35. Otherwise, you end up building an aircraft that cannot transport any passengers. And maybe those who are following me on LinkedIn will are familiar with this image. This shows the curve aircraft efficiency, lift and drag, the ratio between lift and drag versus speed. You have to consider this when you read announcements. They publish the range of the aircraft and the speed of the aircraft as that range could be obtained at that speed. But if this is the maximum L/D ratio, when you are at high cruise speed, the L/D ratio that you use for the Breguet range equation, then the result is different. At a fast cruise speed and at a maximum efficiency speed, you know, there is a difference. There is a 35% reduction of the L/D ratio. This is another tool to better interpret all the announcements that are published on the social network. The L/D max does not depend on altitude, but depends on these parameters, on the wing ratio, the Oswald factor, and the parasite resistance coefficients. And let me make an example. In order to have good efficiency on a pivot, the wingspan should be 38 meters. You see, only in this way you might really increase efficiency. And I mean, the aspect ratio should be 38. Even if you wanted to consider all the ideal parameters, you know, the drag coefficients, you know, you cannot really believe those announcements. This is a tool to interpret. So even if we assume the very high Oswald factors and drag coefficients like 0.25, 0.23, even in those cases you realize that all the press releases that we read are fake. It's very easy, pretty straightforward. So what is my conclusion? We had already seen this. There is a group of values less than 1 that make us lose 15% of range. All the possible combinations of standard efficiency of a GA aircraft, and we were very good at obtaining a very high efficiency. And then the battery mass and maximum takeoff weight ratio better, propeller efficiency relatively good, etc. In all these cases, we are very far from the ranges that are communicated and promoted in the press releases. If you have an aircraft that flies at 200 kilometers an hour at cruise speed, and you want half an hour, reservation or capacity, I mean backup capacity, you can do it, but the values are reduced. So you have to be honest with your customers. When they come and say, why does P-Volt do 110 nautical miles, I have to tell my customers that what they are buying is not true. It's not feasible nowadays. This is another exercise to answer to the question why Tesla does 500 kilometers range and we can't do it with an aircraft. These are the two range curves, Tesla and the P-Volt, without considering, all the rest. At a certain speed, the aircraft has a good range, better than Tesla. An aircraft transporting 11 people has a better autonomy than a 4-seat car. But the range of an aircraft can never equal that of a car, because the drag doesn't allow us to fly at low speed. And in the aircraft, we need to consider the backup for every flight that is planned. We have a certain experience, and we can be very critical, and we can evaluate the potential evolution of these engines. H3PS it's been a very interesting and revolutionary project. We have demonstrated that a hybrid engine can guarantee the same payload on the same aircraft. With the Lycoming engine and hybrid parallel engine, this value is the same. We have also demonstrated that consumptions and emissions can be reduced with this configuration, also because the Rotax engine is much more efficient than a Lycoming. In our latest flight, I was flying a standard aircraft, and our testing pilot was on the HP3 flight. I mean, my consumption was far higher than his, so there is a difference. But can we really say that it can be put on the market? I repeat what Zoltan said, and I also want to speak about money. With the scale economies that we can obtain in our industry, the price would be 100,000 euros versus 30,000. And we have a certain experience. That NASA chose and purchased two P2006 whose goal is not increasing efficiency, i.e. the L-on-D ratio, but the goal is increasing speed. You can obtain that range at a higher cruise speed. This experience is allowing us, also thanks to the support of Royce, to be critical, to be realistic, in terms of our approach to the fully electric aircraft and paying real attention to the real use of an aircraft, you know. If you have a 100 kilometers range aircraft and you want to store it in a hangar, you know, you can't really. There are practical issues, you know, you didn't finish the question, the sentence. Anyway, there are some practical issues with electric aircraft that have to be taken into consideration. And then there is a problem of emissions. Those who produce batteries do not necessarily belong to the group of countries that committed to the emission reduction goals. So this is a cost for us in this part of the world, you know. And then I want to share two images. Professor Marulo and I had not spoken, but, you know, I want to refer to what he said in the beginning. In this month, there are two things, you know. The announcement of Italy and other countries to restart coal power plants, you know. So, you know, it's a way to go back, you know. And then every time I see flight radar, I see these tracks, you know. This means that every day hundreds of flights, in order to avoid rush, you know, they fly, I mean, more hours. Now 12 hours to do what they used to do in 8 hours. So we have to wonder what is really legitimate now. We should also, you know, be peaceful. We can protect our planet only if we are all in peace, if the world is in peace. If you want to download the formula, the presentation, it's a little booklet where I explain all the passages to demonstrate the range equation for electric aircraft. So thank you very much for your attention.
Grazie. Vabbè, ma io ero preparato, quindi...
You know, I knew, I expected it, you know. You have really opened, you know, lots of scenarios, you know. Before the flight by the Wright brothers, the Department of Defense in the US, the Bentley accidents had happened a few months earlier, and they had said it will take a long time before an aircraft flies, but they could fly 2 months later. I understand we all wish it, but based on your explanation, of course, we know that we have to commit to research, but we have only done 5% of what should be done. You know, there's a remaining 95% that is yet to be done. And let me add one thing. It's a technical issue, otherwise I forget it. And April 5, these topics will be dealt with during a meeting organized by the Euroavia students in cooperation with our friends. Students, you know, have an interest in this, you know, so we'll discuss about these issues. So this shows that it is really important that we tackle these issues from an engineering point of view. I mean, we should stop, promoting things on the media. I mean, we have to be honest. Actually, we have to be honest in the interest of the industry as a whole. And for the maths, you can refer to the text. You can download the text, and for the maths, for the formula. But do you have questions, curiosities, comments for our speaker? Is there a comment? Do you have a comment or question? First of all, congratulations, Fabio, for this beautiful presentation. Of course, we can all subscribe to what you've said. I mean, the maths, the physics is there, the batteries, the electric motors can offer lots of things. At Piaggio, we are doing even more. We are trying to interpret the future trends, and the results are not so encouraging for a fully electric aircraft based on batteries. But it's complicated, to reorganize aeronautics and general aviation. The fact is that we do not pollute. I mean, we are not the biggest polluters, but we have to improve anyway. I mean, it doesn't matter, because when the others solve their problems, we will be the biggest polluter. I'm talking about mobility, of course. And it's complicated. It is complicated. It's unclear. But even if we can't really see, we have to explore. We have to explore in many areas, and one area is that of hydrogen. We all know that it is difficult. We know it. And there is no free lunch for anyone, But my question is, are you going to test other solutions based on hydrogen fuel cells, etc.? Because the equation improves. Of course, it introduces a huge problem with hydrogen, of course, but the range might be higher. And then the other question is, I also asked Rotax, and also ENAC said, of course, in the short time, we will have to use sustainable fuels. This is clear in the short term, And general aviation is in a worse situation because general aviation has even less scale economies than aeronautics in general. Anyway, from our point of view, business aviation, the point of view of business aviation, it's not a question of impact, because we do not have an impact, but it's the perception of the customers. Clients are becoming more and more sensitive towards this. They don't want to buy things that pollute. So we can even show that we do not fly on Saturdays and Sundays during the week, etc. But I mean, this doesn't mean anything to them. So is the battery the way to go? And what you showed is physics, is nobody can deny it. If you change physics, let us know, because we would also be interested in to have a better, a more gentle physics. We are back in the 50s when we moved from a valve and a computer to a transistor. Well, we will commit. We will try and do our best. Let me add one more thing. The automotive battery will be developed based on costs improvement and not on range, because in their case 500 kilometers is enough. In our case, it's different. And the battery manufacturers are not willing to invest in aeronautics and general aviation because the market of automotive batteries is much bigger. And that brings us back to the scale economies issue, that issue. So my question is, are you going to continue to study any alternative like hydrogen and tell me, I can give an answer to both questions, hydrogen and sustainable aviation fuels. Well, as far as hydrogen is concerned, of course, we are not passively viewing and watching what the others are doing. So putting aside all that has to do with infrastructure, hydrogen production, etc., because you can also build or manufacture an hydrogen aircraft, but if the client cannot use it, I mean, there's no point. So in this phase, it is very important that we do not launch futuristic plans, but we draw the guidelines. Those who have the know-how to develop fuel cells and the battery pack, the buffer battery pack for power peaks or for hydrogen storage can use. So we have to give them our know-how to develop guidelines so that once they have reliable products, we, as we all have done in our history, we can design the aircraft around what we can find on the market. As far as sustainable aviation fuels are concerned, let me make an example. You know that nowadays the only manufacturer in the world who can provide a fleet for training, one engine and two engine based on Rotax engines is Tecnam. We are the only one who have the IFR certified with Rotax. Do you know what it means for a flight school moving from 40-year-old aircrafts to a Tecnam only fleet? It means that every student from 0 to CPL, commercial pilot license, 150 flight hours, is responsible for 10 CO2 tons less. So if you only want electric fuel, well, you can't. And navigation wouldn't be possible, etc. But if you want to see the true impact of a training fleet on the environment, one pilot that is responsible of 10 CO2 tons less, well, means that there is a 2-year net zero pilot, because every citizen, in the world produces 2 tons of CO2 a year. So we have been the first to certify the Lycoming with automotive fuel. We did it in 2015, 7 years ago. It means that we have removed lead from fuel, the fuel used on the 180 HP Lycoming. And with the P2010, we are already SAF-ready, an aircraft that is already the most efficient aircraft in the world, can already accept sustainable aviation fuel. The problem is that we wanted to fly then, but there's no flight, In Italy, only one refinery offers SAF. Do you know what the content of SAF is? 0.5%. This 0.5% is huge for thousands of hours for air companies that use Rolls-Royce engines, so Boeing, Airbus, etc. But for general aviation, saving 80% of CO2 on 0.5 of fuel is nothing, Let me add something. First of all, you've been very clear. You have explained very clearly that passing to propulsive system able to accept SAF is a first step towards sustainability. We have also done it. Our engine can also accept it. For general aviation, of course, this is fundamental, it's paramount. So having the possibility of accessing to SAF is paramount. And the regulations, the European regulation will make it mandatory. So whether we like it or not, in the next 15, 20, 30 years, we'll have to adapt our products to accept SAF. It is pretty straightforward if you have a turbine engine, but if you have a piston engine, it is less straightforward. And so this is very important to bear in mind. That was just a comment. Yes, interesting. I'm an electrical engineer. Anyway, thank you for your presentation because that was very clear. Behind those figures, because we are not only engineers, we are researchers, behind those figures there are different progress dynamics. Battery density, for instance, in 5-year times with solid-state battery that allowed Ferrari to win in the Bahrain GP, that 150 could be 500, and this is realistic anticipation. With research, that figure might grow even further. So some conclusions should be reviewed. I understand. It is not for the short term, but in the long run, they might be reviewed. So, of course, and that's what we are doing. And this is the reason why on the P-Volt, we chose a swap battery or an easily interchangeable battery to follow, the developments, potential evolution. We would like to sell the aircraft without the battery and to then leave it to an energy provider who has the property of the batteries. We would like to also let them repurpose it, Thinking about 500 kilowatt hours per kilogram in 5 years means betting. It is okay with research, but companies have to design, have to sell aircrafts for profit, We have to consider what is realistic and what is feasible nowadays. We have to sell. We can have a down payment on an aircraft. I couldn't bet with a client. I can't really do that with a client. I can't say, don't worry, in 5 years' time, I will have this value, because that would kill the whole business, Of course, we have to bear it in mind, and we do it with the configuration of the P-Volt. We don't want to stop, but we have to be honest with clients. We can't tell clients, this is the range, 800 kilometers, because in 10 years there will be the necessary batteries. You have to do what's available today and give the clients all the parameters so that they can decide. Otherwise, they buy a fleet, they announce it, and then everything ends there. We like aircrafts that fly and not aircrafts that are you know, in the hangar. Thank you. Congratulations, Fabio. That was really a lecture, a keynote lecture, as we say at university. Of course, the issue of batteries is important. Now we have a problem with gas and oil, but batteries, you know, are based on nickel, cobalt, you know, I mean, these raw materials come from countries that are, you know, not necessarily available. And then there is a problem of costs. Of course, solid-state battery, I understand, but the problem is how much will they cost? Tesla also is expensive, you know. They can afford, like Ferrari, you know, to have a very high price, but it cannot be €1 million a car. So the problem of costs will have to be tackled, and also hydrogen. You know, you have mentioned batteries, the production of batteries leads to CO2 emissions, but also hydrogen, you know. So this is something that should be discussed at world level. So looking at the whole scenario, what do you expect the evolution will be? I can make an example. I didn't bring this graph, I didn't show it, but so in this graph, we have the production of energy in the different countries of the world, so the fossil and the renewable energy part, and the production of battery packs in terms of CO2. So I have identified 3 scenarios: the current energy mix, the scenario imposed by COP26 by 2030, and the scenario imposed by 2050. So 3 scenarios, 3 different energy mix. If all the signatory parties comply with what has been decided, by the year 250, to produce batteries, less CO2 will be necessary, and the battery production, we produce CO2 even before flying the aircraft. With battery aircraft, we have a debt that we have to compensate by recharging, and we have to be careful, because the battery, if the battery can live for many cycles, even if they cost a lot, solid-state batteries can be accepted by clients, because it is the cost per cycle that matters. And also from the environmental point of view, this CO2 emission levels that you have when you have to change battery is repeated every 5,000 flights and not every 600 flights. So it is also the life cycle of the battery that counts. And if you imagine these scenarios, and if you draw the curves, you buy a battery 78 kilograms per kilowatt hour, then I have to recharge a battery. After 700 cycles, I have to change it and then I have to recharge it. And if you also draw the emissions of a full sustainable aviation fuel aircraft, they're always below. I mean, emissions are always lower. For the battery, it is complicated, you know, it is more complicated. Cobalt comes from Central Africa countries where, you know, there are also ethical issues at stake. Nickel and lithium come from countries where the 250 goals are not shared. So, you know, there are lots of factors that have to be taken into consideration. And hydrogen is more promising from this point of view because hydrogen might be produced in countries that are, in a way, amongst those who have promised to, who have subscribed to the 250 goals. Clean hydrogen, you know, might be a solution. But once again, the fuel cell and the reservoir of hydrogen, you know, at present, you know, they're not so advanced, you know. You can't really build or design an aircraft around something that is not really mature. Unfortunately, we couldn't hear the comment. Zero Avia has no battery, but the problem is that one fuel cell that guarantees the peak on a two-engine, you know, plane is a problem, you know. You need a redundancy anyway. Anyway, for the peak power, you know, the battery is recommended. Unfortunately, we can't hear the questions and the comments spoken without a microphone, so we can't hear. Unfortunately, I apologize, we can't hear. So, what is your opinion? The announcement of the Airbus aircraft, you know, not Lilium, Airbus, so zero emissions, you know, they are announcing. What happens? We're talking about general aviation, we're talking about GA. That is less complicated than other segments, you know. Anyway, are these, I mean, no, they're not announcements, you know, they are, you know, investment directions of billion euros, you know. They've been decided by the European Commission. Personally, I would have preferred to see general aviation as a sort of gymnasium because we are smarter, we can, since we are smaller, we can develop faster. Of course, scalability is a problem. I mean, I wouldn't start from the top, but of course, if they are starting from CS25, airliners, etc., but it's research, you know. And when it comes to research, you have to support it. It's always research. Hopefully, it will bring about the results we all expect. Unfortunately, but no mic, no translation.
Maybe not. I'm just switching to English for our friends.
Jumping on the large aviation. because the commission was imposed that this research has to see the impact. There is no way. So the impact means that you have to show that your product, when it will be green, will have an impact on mobility for aviation. If you see the small aircraft, there will be no impact. That was the main driver, why all the research on the small aircraft was put out. Okay? But we know that from technical point of view, this not will be the right way to do. That was clear statement. Eh?
But this is an open question, I know. Yes, yes. We have discussed this point several times. I know, yeah, all together, yes. So I would like to take now this opportunity for thank you, all of you, for coming, for being so proficient as an audience. And another thing that I like to say, that an event organized like this one, with just 3 in-depth presentations, is an event that does not give you time to get bored. So it's so interesting, and the people have the time to explain quiet and precisely, and to answer so competent questions that, well, I have enjoyed it. I hope you too. And I hope to see you again in another time. Thanks a lot.